Hello everyone, welcome to our third lecture of the chapter 1 relation and function. So relation, I will explain it with the example. Suppose A is a pair 1 2 and we have another pair B. The relation is defined from set A to set B such that what it means is we will first find A cross B 1 3. If you want to know that how we are writing A cross B, you can go through our previous year. So in total we have 4 number of A cross B. So by the definition of the relation, we'll go the number of subset. The number of subset is equals to 2 to the power 4 is equals to 16. So that means we will have a total of 16 subsets of A cross B. Now these subsets are nothing but the relation. So I will just write down few subsets. So for example, suppose I will write 1 3 1 4 as the first relation, and then some second relation. It will go on up to total there will be 16 relation. Now I'll briefly also explain how we will draw the arrow diagram. So suppose this is A, here there will be B, 1 2 3 and 4. So we will write this inside a box, and this will be inside a box. Now if I see that my first relation R1 is 1 3 and then 1 and 4, 1 3 1 and 4. So this I will say that what is this? This is my relation R1. So this is just a simple example of how we can draw the arrow diagram. So now we will see how we will find out domain and range as well as the codomain if we have some set. So suppose we have a set A which is 1 2 3 and 4, and we have a set B which is 5 6 7 and 8. So this is set A, this is set B. Now here we have one of the relation such that 1 5 3 and 8 are in pair, and this is R1. So I can write R1 is equals to 1 5 3 and 8. Now what we have to do is we have to find here what is domain, what is range, and what is codomain. So by the definition, what is domain? So domain is all the elements of the set A. So all the elements of the set A which are related to B. So I can write here that domain is equals to 1 and 3. Now we will see range. So range is all the elements of set B which is related to A. So I will write here range, and range I can write 5 and 8. And then we will have a codomain. So what is codomain? Codomain is the complete set B. Now whether it is elements are related to A or not, that it doesn't matter here. All the elements of set B belong to codomain. So in the next lecture we will see how we can represent the relation into the different forms, and we can represent in 3 different forms. One is the roster form, one is set builder, and arrow diagram. So in the exams we will mostly see that it is represented in the set builder form. So by the set builder form, suppose we have a set A which is 1 2 3, and we have set B, and there is a relation. So what does this relation say? Relation says that A square is equals to B, such that A belongs to A and B belongs to B. So we can see that 1 square is equals to 1, 2 square is equals to 4 and 3 square is equals to 9. So in the roster form, how I can write that? 1 and the last one is this one. In the arrow diagram form, again we can write it very simply, like we can write two set A and B, 1 2 3, and here we have 1 2 3 4 7 9. Now we have a relation R. So 1 is related to 1, 2 is related to 4, and 3 is related to 9. So we'll also write what is the domain, range, and codomain. So domain will be 1 2 and 3. Range will be 1 4 9, and all the elements of B will become codomain. So in the next slide we'll have one example. So ARB is nothing, means A is related to B, and we have equation. So what does the equation says? A plus B is less than equals to 3, and A and B belongs to n means natural number. Natural number means starting from 1 to infinity. Okay, so what are the possibilities? So one of the possibilities 1 1, one of the possibilities 2 1, and the last possibility is 1 and 2. So these are the three possibilities, and we can say that this is a set which represents the relation of A to B. Now we will simply write it into the arrow form. We'll make an arrow diagram, 1 2 and 1 2. Now if we'll see the relation 1 1 1 2 and 2 1. So total we have 3 pair inside the set of relation. If I have to write the domain, I can write 1 2. If I have to write the range, it will be again 1 and 2. But interestingly, if I have to write the codomain, it will not be only 1 and 2. Here it says it belongs to n, which is the natural number. For our purpose, we have taken 1 and 2 because this fit inside this relation, but there may be other element also. So here the codomain will be n. Now we will see another example, and here we have a term coprime. So coprime means the numbers for which their highest common factor is 1. No, now I can give some examples, like if we say 2 3, or I say 7 11, or 4 5. So all the numbers which have their HCF equals to 1, we can write them as they are coprime to each other. Now in the question it is given that we have a set A, we have a set B, and we have to write the roster form and the arrow diagram of the relation such that A and B are coprime. So if we know which numbers are coprime, we can directly make a relation between them. First I will write what are the elements of A, which is 1 2 3 and 4. For B we have 2 4 and 5. So for 1 we will have of course we'll have 1 2 1 4 1 5. Like that it will go on, and for 2 also we'll have again 2 5. So I will just briefly write what will be the relation in this case. So we'll start with 1. So for 1 we have 1 along with 2, 1 along with 4, 1 along with 5. And with 4 again I can write only 1, which is 4. So this is the relation such that A and B is coprime. Now we will just recall some of the points that we have written. So number of relations defined from set A to B. We know that the number of relation is nothing but the total number of subset. and if P and Q are the number of elements of A and B, then the total number of subset or total number of relation is nothing but 2 to the power PQ. Now the number of relation defined from B to A, this is also same. Now the number of relations defined on set A. On set A means set A to A. So if the number of elements in A is P, so we can write here as 2 to the power P square. Number of relation on set B, similarly it will become 2 to the power Q square. Number of non-empty relation, so we know that there is only one empty relation, and if we see the total number of relation is 2 to the power PQ, and if we subtract 1 we will get the total number of non-empty relation. Now empty relation we already discussed that there will be always one subset such that it will be empty, and this will also be the one of the empty relation when all elements of set A related to B, this is known as the universal relation. Now we will see the next topic, which is the inverse of the relation. So in simple terms, suppose we have a relation between A and B, so A and B, and we have a relation 1 2 3 and 4 5. So and 2 4. Okay, so relation is defined like 1 5 1 6 and 2 and 4. So this is our relation. So what is inverse of the relation? So inverse of the relation is nothing but if we change the arrow diagram, or I can say that if we reverse the arrow diagram, and the resultant pair which we will receive will be the inverse of the relation. So here if I have to write what will be the inverse, it will become 5 1 6 1 and 4 2. Now interestingly, if you see, then in the first case for R, domain is 1 2, range is 4 and 6, 4 5 6 all. But for the reverse it will be completely interchange, like here domain will be 4 5 6, and range will be 1 and 2. We will have a more clarity with the example. So in the next we will see a previous year question. We have to find the domain of inverse of a relation, which is nothing but the range of the relation R, and in order to solve that we have provided x square plus 3y square is less than equal to 8, and x and y belongs to z. Now what is z? Z here belongs to integer. What is integer? Minus infinity to plus infinity. Okay, so first we will see what are the possibilities that satisfies this equation. Now suppose I will write x is equals to 0, so I can write y within the range of 0 to plus minus 1. If I write x is equals to 1, so I can write y is equals to again 0 to plus minus 1, and if I write x is equals to plus minus 2, then y can again be written in the range of plus minus 1. So these are the only possibilities which will satisfy this equation. If I say the domain and range, so we have to find range. So range is nothing but the values of the y which is related to the x. This is minus 1 0 and plus 1, and this will become the domain of r minus 1. So this will be our answer. Okay, so now we will see different type of relation, and Mostly there are four type in which the relation can be called out, which is identity, reflexive, symmetric, and transitive. And if a relationship satisfies all these three, which is reflexive, symmetric, and transitive, it is known as the equivalence relation. Identity relation on set A is possible if and only if each element of set A is related to itself. For example, we have relation 1, 2, 3, 1, 2, and 3. So if the relationship follows like 1 is related to 1, 2 is related to 2, and 3 is related to 3, so only in this case I can say that it is a identity relation. In the reflexive element also, the every element has to be related with the other element, but here is one catch. For example, I have a relation such that it is a normal identity relation, but also I have one more relation in which one is related to 2. So here I can say that this is not an identity relation, but it is a reflexive relation. But suppose I have another relation 1, 2, 3, 1, 2, and 3, where 1 is related to 1, 2 is related to 3, and 2 is related to. But here one element is empty, so I can say that it is neither an neither an identical relation and nor a reflexive relation. Now what is normal identity relation? This, so can I say that is this identity relation is also a reflexive relation? So yes, all the identity relation naturally it becomes what, a reflexive, but vice versa is not possible. That means a reflexive relation cannot be said to be an identity relation. Now we will be looking into the next type of relation. This is a symmetric relation. So suppose again A is a set 1, 2, and 3. I have a relation 1, 2, 2, 1. So for this particular pair, do I have a completely reverse, that is 2, 1 present? Yes. So this will be known as symmetric. Now suppose I have another relation in which I have 1, 2, and I have 3 and 4, or 3 and 2. So can I call this as symmetric? Which is no. So only within a relation in which we have an equal and opposite pairs present, we call it as a symmetric. For example, if suppose we have 3, 3, we have 2, 1, we have 1, 2, we have 1, 1, then okay, I can say that this is a symmetric, because we have both 2, 1 and 1, 2 which are inverse of each other. For 3 and we can write it as only singular form, and then we have 1 and 1. So null matrix also is a symmetric. So I think this is all for the lecture 3rd, and we will be moving on our next topic in the 4th lecture. So till then, thank you, bye.